Okay, well, welcome, and let's go ahead and get started. I'm sure that there's questions about things that you're doing, so let's go ahead and address those first. Justin?
Yeah, so this may be a little ahead, but on problem 37, whenever you talk about the oblate spheroid and the prolate
Well, I
spheroid,
think that's interesting. Now, these aren't due today, but it's something that maybe we should talk about, because today is not about scaling. We're going to work the other problems today on shift and such. So let me put this up. And can everybody see my screen? Does it look teeny? Does it look okay? Okay, it looks okay. Good. Okay, so I think what Justin is talking about is let x of t be one inside a 3D sphere. In other words, this is a three-dimensional function. The three-dimensional function is equal to 1 inside the sphere and 0 outside the sphere. By the way, I just want to check. Can you hear me well, like I'm using a microphone as opposed to okay, good. And a prolate spheroid, this is interesting because you think if you distort a sphere, that there's only one way to distort a sphere. But that indeed is not the case. There's two ways to distort a sphere. One is the prolate spheroid, which basically takes the sphere and kind of stretches it out on one side, much like a football. Now, a football is not exactly a prolate spheroid, but it gives you the idea of how we distort the sphere. And the other one is an oblate spheroid, which looks like a basketball somebody sits on. So in other words, it's a sphere which is kind of flattened at the top and flattened at the bottom. Now, the Earth, what do you think the Earth is? Do you think that the Earth is not a perfect sphere? Do you think it's a prolate spheroid or an oblate spheroid? Any ideas?
I would say oblate.
It is oblate because of the spinning, I guess. It kind of widens at the axes, and it's more of a oblate spheroid than a prolate spheroid. So my question is, and this challenges your ability to visualize, is how would you distort a sphere in order to get an oblate spheroid and a prolate spheroid? Now, clearly what I'm asking for here is a scaling matrix, right? Because you're taking the sphere and you're stretching it or flattening it or something like that. So I'm asking for a magnification, and we're in doing this, I guess it's implicit I'm keeping the axes the same, so I'm not stretching the sphere and rotating it for the oblate spheroid. Okay. um, the axes are exactly the same, so we just have to scale on one axis. So Justin, is that correct? And if so, what was your question?
yeah, so my question was like, whenever you're saying making the oblate spheroid, um, whenever you compress it like vertically, does the horizontal dimensions expand, kind of like holding its area, or
Well, yeah. Well, I would think of it as if you do not scale one or more of the dimensions, you're scaling that dimension by one. Or if you remember the Markman hearing, we are magnifying it by one. Okay. So we're leaving it as is. I don't know if that answers your question or not.
yeah, I think so. So like you're just compressing it vertically. The horizontal like axes aren't being affected by
That's
scaling.
correct. And clearly there's more than one way to get an oblate spheroid. You can have a football like this, you can have a football like this, or you can have a football like this, right? So there's more than one way to get the prolate spheroid. And there's more than one way to get an oblate spheroid too. Okay, does that help? Okay. And basically, I just want an explanation of what this scaling matrix is. I just like an explanation of it. There isn't a unique answer, but I think that we can come up with a general idea of what's happening. Is that okay? Okay, excellent, excellent. Okay, you know what I forgot? I forgot my random number generator today. So I am going to have to come up with a random number generator here somewhere. Let's see. I will be right back with a random number generator. Okay, so I have my 3 coins for the random number generator. I like, uh-oh, I dropped a bit. There it is. I'd like to share with you what we're going to use today for the random number generator. And these are really old, as you will see. This is I don't know if you can see it, but it's a Deutschmark. So this is a German mark, and of course, Germans don't use marks anymore. They use what?
Euros.
Yeah, euros. So that's really old. I used to like my last name because it meant German money, right? Robert Marx. Then we have a very nice Australia coin, and this Australia coin has a picture of Queen Elizabeth on it, as do all of the Commonwealth. And then this will make Glauco happy, even though they're not used anymore. This is a Spanish coin from Spain before they went and applied the euro. No, maybe this is not Spanish. Wait a second. Juan Carlos. No, it isn't. No, España. Espana. Isn't that Spain, Glauco?
Yes, España. Yeah.
Okay, so yeah, it is it's a Spanish coin. Okay, so we have 3 bits. Okay, so let's go to these. I've asked you to all prepare to show your work. So let's see. Let's do Chris as, don't be mad, Chris, 0. David is 1. Glauco is 2. Adam is 3. And Justin is 4. And who am I missing? Somebody fell off the end here. Oh, Aiden. Aiden, you're 5. Okay. So here we go. I'm shaking the random number generator. And this is for problem, let's see. Problem 32. Problem 32 is tails, tails, heads. So that's number 1. David.
All right.
Thank you for not having one of those big foam rubber fingers that say you're number 1. Okay, go ahead. Okay, this is what? 32. Okay, I'm going to quit sharing my screen, and I'm going to give you permission to share your screen. Okay.
Okay. Oh, okay. Let's see.
Okay, now you're allowed.
Disabled participants.
No. You're not giving
there.
Not giving this guy time to hunt and click. Most of my life now is hunt and click.
All right.
First of all, explain the problem.
Okay, so yeah, what is the Fourier transform of this 3-dimensional function, which has sync in 1 dimension, rectangle in another dimension, and e to the scaled t squared in another. So the sinc transforms to pi and pi to sinc, and
I would call that a Gaussian.
yeah, okay, yeah. So Gaussian to Gaussian, and with some shifts, and then I somehow I forgot that this was also to be illustrated.
No, I don't think I asked you to sketch it. No, I didn't
Oh,
ask you to
okay.
sketch it. No, I don't think
Okay.
so.
Okay.
Yeah, that would
That's
have you would have hurt yourself, I think. Well, you could have done it in MATLAB or something like that. So, okay, go ahead and stop sharing your screen. Yeah, this is obviously application of the separability theorem and makes use of the Fourier transform. You know, Gauss, for who the Gaussian is named, was an incredibly prolific mathematician. And if I ever explained the first problem, I remember explaining it, but I don't know if I did it in here, that Gauss solved in elementary school that he was proud of his whole life. Well, as punishment in grade school, Gauss's teacher said, okay, everybody, you've been bad. I want you to add up the numbers 1 through 100. And Gauss sat down and thought, and he did it in his head, and he gave the answer like in 20 seconds. And he was very proud of the way he did it. You know, classic math way of doing it. Does anybody have an idea how Gauss did it? Go ahead. Somebody said, somebody breathed.
Yeah. Let's see. 100 plus 1, 99 plus 2, and so on,
okay.
down to 50 plus 51.
You're out of phase, David. You're out of phase. You have the right idea. 99 plus 1 is 100. 98 plus 2 is 100. 97 plus 3 is 100. So how many things of these hundreds do you have? Well, it's all the way from 1 to 49. So that turns out to be what, 4,900? Then you add the 100 that you didn't add. So that's 5,000. And then you didn't add the 50 in the middle. So that's 5,050. You see how he did that in his head? Really smart guy. And he was kind of proud of that most of his life. Yeah, he was an incredible genius. Okay, let's take a look then at the next problem that I gave you, which is what is the Fourier transform of, well, let me share it here. What is the Fourier transform of, and this is going to be important when we talk about tomography, by the way, in the central slice theorem. Tomography is the reconstruction of signals from the projections. So you'll need to remember this for that topic, which is coming up. So you have a two-dimensional function, which is only one-dimensional function. And how do you express that? So let's go ahead and generate the random number here. Let's see. Ooh, 3. Who's number 3? Okay, Adam, take it away. Oh, you're a paper hog, Adam. You don't like to waste paper, do you?
Usually I do, but I realized this all could fit on one, so I went ahead and did it.
Okay, I need to make my homework more difficult then. Okay, if you can fit all the homework on one sheet of paper. Yeah, this was pretty simple in a number of places. Please go ahead.
So yeah, so you can equivalently say that this is a rectangle of T1 times 1. So then when you transform it, you get the sinc of U1 times the delta function of U2. So then it is just a sink along the U1 axis and zero elsewhere.
Yeah, and along the U1 axis, it's kind of a modulated delta sheet, isn't it?
I suppose,
Yeah, del of U2 is something which runs down the U1 axis, and it's just a big knife edge, and we're multiplying that by a sink in order to give it structure. Okay, thank you. That's really simple also. Go ahead and unshare your screen if you would. The next problem is to find out the Fourier transform of a rectangle in 2 dimensions, and where pi 1, man, this is too easy. I don't know why I assigned this. This is too easy. But you guys are coming up on Thanksgiving break, and you need a break, right? So let's see, heads 110. What's 110? 6? Aiden.
I'm 5, but I'll go.
Oh, you're 5. Who was 6?
I don't think there is a 6.
Oh, there is not a 6. Okay. Never mind. Oh, we got 1 again. And now we have our random number generator said 4. 100. Who's 100? That's Justin. Okay.
All right, y'all see my screen?
Not yet.
No? Oh, okay.
There we go.
Okay, so yeah, so this function you can take, it's just two different functions that are shifted in time, and you can use separability to take the Fourier transform of each one, and the function of T1 can shift to be a modulated sink, and the function of T2 is also a modulated sink that is modulated at a different amount. And then plotting this was kind of interesting, so I just used Wolfram to show the plot.
Really? That's that little thing over there on the right?
Yes.
Now, it looks weird in the middle. It looks like a crater.
Yeah, it's because they cut off the plot at 0.2. That continues to go up to 1.
So this thing still pokes up. And you're probably not plotting the Fourier transform. You're probably plotting the magnitude of the transform or something, right?
Mm-hmm.
Is that right? Okay. This is very interesting, by the way, because you remember we saying that that the Fourier, okay, thank you. Go ahead and unshare your screen if you wouldn't mind.
Okay.
Perfect, by the way. We mentioned that the far field in a diffraction pattern was related to the Fourier transform of whatever the aperture was. Now, we've seen the Fourier transforms themselves can be complex, right? But guess what? Your eyeball doesn't see things that are complex, does it? Your eye does not see things which are complex. Your eye only sees something that's real. So what does your eye perceive? We will talk about this a little bit later on, but what your eye sees is the electric field, which is complex. That's all the e to the j's and things like that. But it sees the magnitude squared of it. Your eye is a square law detector. And any time that you see the magnitude squared of any measurement, that's referred to as a square law detector. So our eyes can't see phase. It turns out, if you remember electromagnetics, what was e to the jkz? Do you remember what that was? E to the jkz was a plane wave just propagating down the axis, right? Just a plane wave propagating down the axis. What if I did a e to the j alpha x, e to the j gamma y, e to the j alpha x plus beta y plus gamma z? Well, that turns out, and maybe we'll have a time to talk about this. This is not an e to the jkz, but it is a It's a plane wave coming in a different direction, right? So that's what the different e to the j's stand for. Now here's the question: if you see a spot on the wall, say from a laser printer, can you tell the direction from which it came? Now we could cheat and we say, you know, it's at an angle if instead of a circular cross section, it's an oval cross section. But let's put that aside. We want to look at the light itself. And once we look at the light itself, can we tell anything about the direction from which it comes? No, you can't. You can't tell it. All you can see is the magnitude squared of it. And e to the jkz, what's the magnitude squared of that? 1, right? So that's what you see that's what you see when the e to the jkz hits the wall and you see an image of it. What about e to the j alpha x plus gamma y when you hit the wall? It still has a magnitude of 1 and it looks exactly the same. You can't tell the direction from which it comes. So when the plot came, we saw the magnitude, and that's pretty indicative of what we see. And just remember, we are square law detectors in terms of magnitude. Our eyeballs are square law detectors. We detect the magnitude squared of the electric field in antenna theory and such. Okay, thank you. Let's go to the next one, the next problem. And what was the next problem? Okay, the next one. Oh man, are these softballs? I feel like I'm at a Joe Biden debate. These are really easy. Okay, 1, we did 1 already. 0.
That's me.
That's you. Okay. I will unshare my screen.
Okay, can you guys see this?
Yes.
Okay, so 35. So we start with the definition, definition of the multidimensional Fourier transform, which is just this guy right here. Then we can negate U, which.
Oh, I'm sorry. I did the wrong one. This is.
Am I in the wrong
I skipped
place?
one. No, you're on the right one. I was on the wrong one. This is to show that if a signal is real, its Fourier transform is conjugately symmetric. So go ahead.
Right.
Chris.
Okay. So if we negate the U, we lose the negative sign in the exponential. Then if we conjugate both sides, what we'll get is a conjugate of the integral. We can move the conjugate inside the integral and apply it to the x of t. But since x of t is real, it's equal to its conjugate. Then also we'll get a negative sign on the exponential. So we get this term right here, which we can recognize as the Fourier transform, which is equal to x of u.
Okay. Very simple. Thank you. Go ahead and unshare your screen. I think everybody probably got that. This is very interesting because if you think about all the Fourier transforms, you see them in one dimension. If you look at the magnitude of them, they're all even functions. And because all of the signals that you're transforming are real. If you Fourier transform a real function in higher dimensions, it turns out if you take the function, whatever it is, flip it around one axis, flip it around the other axis, flip it around the third axis, flip it around the fourth axis, you flip it around all of the axes, and then you conjugate it, you get the same thing you started with. And that's just a consequence of the definition of the Fourier transform. That's the conjugate symmetry. It's the generalization of the idea of being real. Okay, let's see if I can get this right this time. Now we're going to go to 36. And this is the one I wanted you to work in a special case. You didn't need to work it in that case, but you'll notice we have two functions here. We have the sinc and we have the cosine. And both of those are a function of T1. So how do we handle these things? So let me get how many have we worked? Who's left? Who hasn't done anything?
Glauco and I.
Glauco and, I'm sorry, who, Aiden?
Aiden.
Okay, we're going to flip a coin. Glauco, your heads, Aiden, your tails, okay? That's tails.
Sounds good. Okay. You can hear me, right?
Yes,
Yeah, I'm not muted.
hear
Okay.
you very well.
So I started by separating the functions, and I wanted to just deal with the functions of T1 first. And I used Euler's formula to redefine cosine as such. And then what I did was I decided, okay, now it's time to Fourier transform this. And I split it up into two because there's an addition sign, so I split it up into a sinc times e to the j2 pi t and sinc times e to the negative j2 pi t. And this looks like the sinc. This looks like the Fourier transform of a shifted rectangle, so I figured I should use a duality theorem here, so that's what I did. I took what I knew, if this were a function of u, I knew this would be the Fourier transform. This would be the original time function, so I just plugged in negative u because that's what the duality theorem says. And so what I figured is that the Fourier transform of this is, of this term here is pi negative u plus 1. And the Fourier transform of this is pi negative u minus 1. But because pi is an even function, it doesn't matter if the u is negative or positive, because when you flip it around, it's the same because it's
Yes.
symmetric. So that means when I add them together, I just switched it to a normal positive u, which means the function of u, when you Fourier transform it, is two shifted pi functions that have been shifted in opposite directions. And then the Fourier transform of the function t that's in terms of t2 is just another pi function. And so you multiply those two together and you get this as the Fourier transform. And then this graph is wrong. I realized that just a minute ago. It's the same. It's the right shape, but it should be, both of these squares should be centered around negative 1 and 1.
Negative 1 and 1. Okay. Okay.
Yeah.
Great. Great. Thank you, Aiden. Go ahead and unshare your screen. Yeah, this is a very powerful way to think, by the way. Let me illustrate this. Okay, let's see if my little whiteboard works here. Yeah, it does. Good for me. You know, what happens when we take a baseband signal x of t? This is communication theory 101. And this baseband signal has a Fourier transform of x of u. And this is a baseband signal. And so as a function here, we have something, say, from minus b to b. And that's supposed to be Hermitian. And the way we modulate it, at least fundamental modulation 101, is we multiply x of t times the cosine, right? Cosine of 2 pi, whatever the carrier frequency is, times nu of t. And the cool part about that is that the cosine of 2 pi nu t has a Fourier transform of a couple of delta functions. Let's put a 2 out here just to get rid of the 1/2, if you will. E to the plus j, well, I'm sorry, nope, wrong. Put a 2 out here. But it has a Fourier transform of del of u minus nu, del plus del of u plus nu. What's new? It's a joke. Nothing. What's new with you? Okay. So the point is that you know what? If you tell a joke without a laugh track, it's not funny. You have to put a laugh track. I'm going to go back and put some sort of laughter in the audio for my lectures here. So here's what we get. We get b times b times, I'm sorry, convolved with, since we're multiplying in the frequency domain, something like this, which goes from minus nu to nu. And that gives us the replication of the spectrum at minus nu and nu. So this is how you heterodyne, or you take baseband signals and you extend them to higher dimension, or I'm sorry, you extend them. You take baseband signals and you heterodyne them up to be centered around a frequency carrier. Now, trying to look at the whole trying to erase everything. Clear. Okay, clear. Okay, so we have the same sort of thing with two dimensions. Now we have a sinusoid. What's the cosine of 2 pi nu 1t in, let's say, t1? What does that look like in 2 dimensions? That's the question. Well, I think you can see that it kind of looks like, I can't draw it perfectly, but it's kind of, man, that's terrible in terms of a straight line. It kind of looks like a cross section with is a sinusoid, right? And remember, we take this sinusoid and we smear it down the T2 axis. Remember, that's how we took a 2-dimensional function and made it into a 1-dimensional function. And so if we multiply this cosine times an image, and the image has a Fourier transform of x of u1, u2, just like in 1 dimension, what we're going to do is we're going to take that 2-dimensional function, which might be a baseband signal here, if you will. And now we're going to be centering this at where? Nu1 is equal to v1. And also minus nu1. Because the Fourier transform of this cosine is a bunch of Dirac delta, or a Dirac delta here, a spike, if you will, right? It's a 2-dimensional spike. And we're convolving it with this, so that means we get a replication of this baseband signal at these values of u1 and u2. And what happens if we rotate this thing? If we rotate the cosine? Well, it turns out it rotates the Fourier transform also. But the important thing to think about this is that in 2 dimensions, when you multiply by a cosine, you have the same thing happening. You have the baseband signal kind of replicated at the plus and minus frequency of whatever the sinusoid is. And that's very interesting. Turns out to be a foundation of classical holography, which we won't get into here, but that's a very neat way of thinking about things. So anytime you can think about things, that's good. Now, something we haven't really talked about, what is del of t? We haven't talked about that, but this is basically del of t1 all the way up to t sub n. So in 2 dimensions, del of t what the heck was that? Del of t in 2 dimensions was equal to del of t1 times del of t2, right? So let's look at that. This is supposed to be a delta of t in 2 dimensions. Well, if we look at t1 and t2, If we look at T1 and T2, what is del of T1? I say it's a big knife edge going down here, right? It's a big knife edge going down the T2 axis. Does that make sense? Because it doesn't matter what T2 is, as long as T1 is equal to 0, you get infinity. You get a Dirac delta. In a similar sort of sense, you get this for delta of T2. You get a knife edge which is going down the T1 axis. Now, if you multiply these two deltas together to get the two-dimensional Dirac delta, you get 0 everywhere except where the intersection is. And where the intersection is, you get a big spike. So that's what it looks like. If you have T1 and T2, and here's the axis here, this is del of T1 times del of T2. You get a big spike, a big Dirac delta spike. Trying to draw a spike here. You get a big Dirac delta spike at the origin. So that's how we interpret the two-dimensional Dirac delta. Is that okay? Okay. No questions. Let me go ahead and return to the lecture then. And I will stop sharing my screen. I don't want to stop sharing my screen. I want to put up chapter 8b. Okay, hopefully you can see this. I believe this was the last slide that we ended up on last time, where we talked about rotation. And we talked about rotation and the order of rotations and transpositions and things of that sort. And for homework, I ask you for a bunch of operations, whether these operations are commutative. It's a really, I think, kind of interesting thing to look at because it's so fundamental to everything. Does rotation translate, or does rotation commute with shifting? Does rotation shift with, or does rotation, does it matter whether you rotate and shift or shift and rotate? Does it matter? Okay, well that's for next time. So we'll look at that next time a little bit. Now I want to talk about something that also doesn't happen in 2 dimensions. That's the idea of circularly symmetric functions. A circularly symmetric function can be thought of something. You guys are probably too young to remember what a record player is, or even a DVD player. But you have this little disc that spins around, right, and goes around in circles. Well, if something goes around in circles and you look at it, you can't tell whether it's moving or not. It's a circularly symmetric function. So if you spin a circle, no matter how you spin it, it still looks like a circle. And if you take this annulus, this donut-shaped thing here, if you take this f of r, then this is a this turns out to be a donut. That's also circularly symmetric because if you spin it, it doesn't change, right? So we would expect that maybe this 2-dimensional Fourier transform changes in some sense if we have, oh, I noticed something here. Ah, there we go. Get the T2 on top. There should be something special happens with the 2-dimensional Fourier transform, and that's what we're going to look at now. It turns out that in 2 dimensions, if you have a circularly symmetric function, let's see if we what happens to the Fourier transform. So let me ask you this. Again, visualize the far field for those of you that have had antenna theory or acoustics, where you have a transmitting aperture and the far field is the Fourier transform of the aperture. Is that okay? So we have a aperture here and we have a Fourier transform out here. If you turn the aperture, what do you think happens to the Fourier transform? We've already addressed this, haven't we? The Fourier transform, we've found out by looking at the rotation matrix, also rotates with the aperture. What if the aperture is circularly symmetric? Well, if you spin the aperture and it kind of stays the same, that means that the Fourier transform is always going to be the same. Does that kind of make intuitive sense? So what we're going to find out is that if we take the Fourier transform of a circularly symmetric function, we get a circularly symmetric function. That circular symmetry is preserved upon the Fourier transformation. Now, in order to look at the math of this, we look at these substitutions below. We're going from regular rectangular coordinates to polar coordinates. And if we do that, we see that what? T1 is equal to R1 times cosine theta. What are we talking about here? Well, we're talking about a vector here that has a value of T1 on this side, and over here has a value of T2. So we're looking at the location of this point. Well, the location of this point can also be made in polar form if we give this radius, this in polar coordinate radius, the length of this vector, and we look at theta. And we look at theta as the angle that we measure counterclockwise from the T1 axis. That's just going to be our convention. And I think you can see from trigonometry that there's two things that happen. T1 is equal to R times the cosine of theta. Is that okay? And T2 is equal to R times the sine of theta. Is that okay? Because T2 is equal to the side of this triangle. That's T2. T1 is the side of this triangle. Or yeah, T1 is the value here. So we have these substitutions. And then if you remember from fields, the differential dt1 times dt2 can be written as RD theta. Do you recall that from somewhere in your electromagnetics past? I hope so. So we're going to make those variable substitutions, and we're going to assume that x of t is equal to f of r. Now, of course, r, if we wanted to go back to polar coordinates, is equal to this, is equal to the sum of the squares of the rectangular coordinates, right? R is equal to that. So we have these substitutions, right? But we can also go into the frequency domain. We have a T1, T2 domain. And in the T1, T2 domain, we have R and theta. We can also do that in the frequency domain where we have a U1 and a U2. And we better call it a different variable, so we're going to call it rho. And we're going to call the angle here phi. So we're also going to take the frequency domain and we're going to make that into polar coordinates also. Is that okay? And that is indicated by the values which are shown at the bottom of the page. U1 is equal to rho cosine phi. U2 is equal to rho times the sine of phi. Same sort of thing. So, okay, that's all well and good. Let's see how more dangerous we can get. Okay, we start out with the Fourier transform. That's our regular old buddy, the two-dimensional Fourier transform. And what's the dt d2 equal to? That's RD theta. Right, that's what we said. And what is the U1 equal to? Well, it should, first of all, there should be two integrals here. So this is equal to the integral. We said x of t1 and t2 is going to be circularly symmetric, so we're just going to bit a function of r here. And then we get e to the minus j 2 pi times u1, which is rho times the cosine of phi1, times r, let me put the r out here, times the sine of phi1, sine of theta 1, or no, just sine of theta, plus rho times r times the, no, this is wrong, isn't it? Let me do this again. U1 is equal to rho times the cosine of theta, or cosine of phi, I should say, because those are the coordinate and the frequency domain. The T1 is equal to r times the cosine of theta, right? And similarly, we have down here minus rho times r, and now the only difference here is we have the signs. And this, of course, has the values of r d theta. And since we're integrating over different intervals, the integration limits don't go from minus infinity to infinity. It goes r is equal to 0 to infinity, and then theta is equal to 0 to 2 pi.
Dr. Marks,
Yes.
where did the minus sign come from?
Which mine? Oh, it came from Detroit. Okay, that's a joke. It's a family joke. My kids used to come to me and said, they would say, "Daddy, where'd the light go when the light goes out?" And I says, "Well, it went to Detroit." And they went, "Oh, okay." So whenever we question where something went, I always said, "Well, it went to Detroit." And I have no idea why we chose Detroit, but that's kind of a family joke. So we have this, and let's rewrite it in a little bit more friendly way. Thank you for pointing that out, Adam. I appreciate it. Notice the R rho is common to both of these. Okay, there we go. So I've simplified it a little bit. Now, if we look at it a little bit, what does this thing inside the parentheses look like? I don't know, but it sure looks like some sort of trig identity, doesn't it? Yeah, the thing in parentheses sure looks like a trig identity. Well, it is a trig identity. And I think there should be a minus here. Actually, it doesn't matter. But it's equal to the cosine of theta minus phi. So I've simply rewrote this equation, putting the cosine of theta minus phi there, RD theta. And that's what the trig identity is. Now, we're going to need a little bit of explaining here because we're going to nest the integrals. And you notice that the only thing here that is a function of theta is this, right? That's the only thing which is a function of theta. That's the only thing in the integration which is a function of theta. And notice we're integrating from theta is equal to 0 to 2 pi. We're integrating from theta is equal to 0 to 2 pi. So this is the cosine of theta minus phi. This is a periodic function, right? What is the period of this function? Period of this function is 2 pi. So it doesn't matter if I have a periodic function, say a cosine, and I integrate over a period here. Isn't that the same as integrating over a period here? We talked about this before, but in terms of when we looked at the one-dimensional Fourier series. But the idea is, yeah, you integrate over any period. Start anywhere you want to, and you can integrate. And boy, where did I went to Detroit? I guess. Okay, you can integrate over any period that you want to, and you still get the same thing. It doesn't matter what the phase of the integration is. Doesn't matter whether you start or stop. Well, you notice phi here is just a phase. That tells you how much the cosine is shifted, right? Phi tells you how much the cosine is shifted. Once you shift it, you still integrate over a single period. Once you shift it, you still only integrate over a single period. So I maintain, let's get rid of the phi. As long as we talk about this periodic function cosine of theta and we're integrating over a single period, then these two things should be exactly the same. So we can get rid of the phi. Now there's something interesting that happens here that goes back to our example of a diffracting aperture and the far field, which is the Fourier transform. We say that if this is a circularly symmetric function, the far field can be a circularly symmetric function. We don't have to work any farther to see that this is indeed the case. If we have a circularly symmetric function that's a function of r, the result is always only going to be a function of rho in the frequency domain, right? The frequency angular variable phi is gone. We made it go away. And because it's gone, we can assume that since none of this expression here, whoops, where'd you go? Go away. That nothing in this expression is a function of phi anymore. The phi went away. The phi was just the shift of the cosine. So because the phi doesn't exist anymore, I don't care. Once we integrate this thing, no matter what we get, it's just going to be a function of rho. And if it's just a function of rho, the far field is going to be circularly symmetric also. So we see immediately that our intuition is salved, and we have a result which is very nice. So it does turn out that if we have a function which is circularly symmetric, then its Fourier transform is just a function of rho. It's just a function of the radial variable in the frequency domain. Okay, so here's the reason we use Bessel functions. Let's go back to the original expression here. And I'm going to nest this, by the way, as the integral from r is equal to 0 to infinity. And then the integral over a period. I'm sorry, at theta. The integral over a period. Now, this period can be any period since this is a periodic function. So this theta can go, instead of from 0 to 2 pi, it can go from minus pi to pi. We don't care as long as it's over a whole period. And then we get a e to the j 2 pi r rho times the cosine of theta d theta r dr. So I've switched around integration signs and I have this very beautiful result here. And here's the thing, that integral that I have brackets around is something that is not a function of, whoops, what did I forget? I forgot something, didn't I? I forgot the function we were Fourier transforming, the f of r. So the f of r should go in there. But notice this integral is not a function of r. It has nothing to do with what we're Fourier transforming. So why can't we analyze this for all cases and simplify it? Well, how do we simplify something like this? Well, could I convince you that I can change this to a sign?
Wait, why does the r in the exponent not make any difference?
No, I'm not saying the r doesn't. I'm saying that this function, this integral over theta, is not a function of what we're transforming. That's what I'm saying. It's something that this term occurs no matter what we're doing a two-dimensional Fourier transform of, if it's circularly symmetric. And so it's something that we can evaluate in closed form. And to do this, again, why can I put a sine here instead of a cosine? Because that's just shifting the frequency, or shifting the integration limits. We're integrating over a period. So the integration of over a cosine is the same as integration over a period of a sine, and they're all the same thing, right? And then we come down here, and where do we get this? Well, it's one of these identities we look up in, I don't know, Wolfram's Math World or something like that. And it's a relationship for, this integral, and this integral turns out to be a Bessel function. Well, notice if we set n is equal to 0, and we set the z is equal to 2 pi r rho, then we have exactly what we need in order to evaluate this integral in closed form. Does that make sense? And I think you can see that if we set this as a 0, this integral is going to integrate to something like j sub 0. It's going to be a zeroth order Bessel function of the first kind. And if we fill in the details, using this, we get the following result. That f of r Fourier transforms, the circularly symmetric function f of r Fourier transforms to a Fourier transforms to f of rho, and also a circularly symmetric function, which is given by this integral. It's given by this integral. And that is really, really nice, because this is something called a Fourier Bessel, or a zeroth order Hankel transform. It's the relationship between two functions. It relates the circularly symmetric function, in the T1, T2 plane to the circularly symmetric function in the U1, U2 plane. And I have heard it more commonly referred to as a Hankel transform. Now, let's step back a little bit. We have a circularly symmetric object, right? Maybe a circle. Now, we want to compute the Fourier transform of this circularly symmetric object. Under the assumption that this is a function just of r, the radial variable in the T1, T2 domain. Notice this is the same thing as a function of the square root of T1 squared plus T2 squared, right? It's the same thing. There's two ways to do it. Number one is to go right to the Hankel transform and just use the Hankel transform. And whatever we get out of here is what we're going to get, the result that we're going to get over here, which is going to be the Hankel transform. So we could integrate using the Bessel function, or we could go down here and we could use the regular two-dimensional Fourier transform that we all know and love, and instead put f of square root of T1 squared and T2 squared in there. If we use this second technique, you will get exactly the same answer as you get with the Hankel transform. It's just that this is usually easier to evaluate than cranking through all the math here, or even entering it into the Wolfram integral calculator or whatever. Okay? Plus, it gives us another transform to play around with. The Fourier Bessel or the Hankel transform. In fact, I would submit to you that using the Hankel transform is always easier. Using the Hankel transform is always easier than using the two-dimensional Fourier transform, except in one case. And I'll talk about that case just in a second. So always use the Hankel transform if you're doing circularly symmetric objects. It's much easier. What's the case where the two-dimensional Fourier transform is easier? The exception Anybody guess what the exception is? The exception is the Gaussian, because for the Gaussian, we can write it as a separable function, right? And we know that this Fourier transforms to, and I'm going to skip a step. Well, no, I won't. E to the minus pi u1 squared, e to the minus pi u squared, which is equal to e to the minus pi rho squared, right? So we evaluated this using the separability theorem, but this is the only place I know where you should use a regular two-dimensional transform instead of a Hankel transform. But it does tell us something, and I'll give this to you as an illustration, if you will. The Hankel transform Can anybody tell me what this integral becomes? We have somebody going for the mute button. Okay, Adam.
It should be the same answer in the end, right?
It's the same answer, because it doesn't matter if you work it out with the Hankel transform or the two-dimensional Fourier transform. You get exactly the same answer. This is e to the minus pi rho squared. We worked it using separability up here, and that's going to be exactly the same thing that we get down here. And again, this Gaussian, this two-dimensional Gaussian is the only case of which I know where applying the two-dimensional Fourier transform is easier than applying the Hankel transform. In all other cases, applying the Hankel transform is a better and more easy. So let's do our first Hankel transform, if you will. This is a two-dimensional Fourier transform of a circle. We're using a pi function. Well, remember what the pi function was defined as. It was defined as 1 as long as r over 2 is less than a half, right? And it's equal to 0 if r over 2 is greater than a half. Remember, that is the definition of the rectangle function. Well, this is the same thing as saying that r is less than or equal to 1. The magnitude of r is less than or equal to 1. Of course, r can't go negative, can it, in polar coordinates? R is always positive. And over here, we have the same thing if r is greater than 1. So this f of r is a circle of unit radius. I'm sorry, let's see. Unit radius, yes, unit radius. So it goes here to 1, 1, minus 1. If I could draw symmetrically, this would be a minus 1 also. So it's a unit circle, and it's equal to 1 inside the unit circle, and it's equal to 0 outside the unit circle. We okay? So let's look at the Hankel transform. We have f of rho is equal to this result. This is the general Hankel transform. And we're going to put in the idea of a circle. Now, the only thing with the circle is we don't integrate from 0 to infinity. That rectangle limits our integration from r is equal to 0 to the edge of the circle, which is 1. So we only integrate from 0 to 1. And within this interval, the circle is equal to 1, so we don't have to do anything. So we get the integral of 2 pi r j naught 2 pi r rho. Now, how do we evaluate this integral? You take it to Wolfram integral evaluator, unless you know how to manipulate Bessel functions. Well, here's another one of those elements, or one of those identities of the Bessel function, and this means that the integral of alpha j naught alpha, if we do an antiderivative, is equal to alpha j1 alpha plus a constant, right? Man, that's a terrible. Let me try that again. Do you agree that this is just the antiderivative statement of the same result? Here's the takeaway. This integral, which is r j2 pi r rho, is going to integrate to something which is like a j1, right? It's going to integrate to a j1. If one does all of the variable substitutions correctly, guess what f rho turns out to be? It turns out to be a j1x over x, which we know as our old friend, the jink. The Fourier transform of a circle is a jink in 2 dimensions. Interesting, right? You can see why it's called a jink now, because, well, what's the deal? If you Fourier transform a rectangle, you get a sink. If you Fourier transform a circle, you get a jink. So it's a j1x over x sort of function. And this is what it looks like. This is f of rho is equal to 2 jink of rho. You know, you look at this, and if I took a sink function and I rotated around the record player, or if I spun it around, it would look kind of like this, right? In the same way that the jink kind of looks like the sink, right? You might have heard this earlier referred to. You might have heard this referred to in physics as something special, because it is something which is talked about in physics. And that's the Airy pattern. If you remember, Airy pattern was the diffraction of a circular aperture into the far field. It's the diffraction of a circular aperture into the far field. And does anybody remember what this middle thing is called? I hope they still teach this stuff. What the meat of this is referred to. Has anybody heard of that? No, nobody's heard of it. Wow. Okay. That middle of it is referred to as the airy disk. That's the middle of the Jink function of the far field. Anybody ever heard of the airy disk? Apparently not. Okay, well, okay, trying to jog your memory. Well, that basically concludes the lecture this time, and I'll be adding some homework that hopefully we can talk about next time. But before we go, are there any questions? Okay, either I've been very clear or very opaque. We'll find out next time. Thank you very much.
Thank you.
Everybody take care. Bye-bye.